In this video, we're going to use a multi-layer perceptron, which is a type of neural network, to classify an incoming sound as either a trombone or an oboe. Neural networks can be used for a lot of different things. Classification is one of them. And when we do classification, we are predicting or identifying or categorizing or classifying which category an input belongs to. And in this case, as I said, our categories are going to be trombone tones and oboe multiphonics. One reason why we might want to do this is if we have a live performance, maybe involves improvisation, and we want our computer or machine to listen to the incoming performers, in this case, maybe a trombonist and an oboe player, and identify which one is playing at a given time. So the way that we're going to do this is we're going to get a collection or a corpus of trombone sounds and oboe sounds. Here we're just going to use sound files of different recordings of trombone and oboe. And we're going to first take all of the trombone sounds and do an audio analysis on them. For example, one could do analysis like pitch, the brightness of the spectrum, the noisiness of the spectrum, these types of audio analyses. And we're going to send those to the neural network as the input. And at the same time that we're sending that input to the neural network, we're going to also be telling the neural network with a label which instrument these analyses are from. So we're going to be sending the analyses in as input and saying, this analysis that I'm showing you right now, this is an example of a trombone. And then we're going to do the same thing with the oboe samples. We're going to use the same audio analysis, send those analyses to the neural network. And when we send it those analyses, we're going to say, this example that I'm sending you right now, this is an example of an oboe. And then once it has all of these examples, it has all of the oboe examples that are labeled oboe and all of the trombone examples that are labeled trombone. Then the neural network is going to sort of make a guess on each one of these examples that we've shown it, and then check and see if it got the answer right, or if it got the answer wrong. And if it got the answer wrong, then it's going to make a slight adjustment so that next time it sees that example, it can be a little bit more accurate. And this is how training works. And after making these guesses and slight corrections thousands of times, it'll be a lot better at making those predictions accurately, so that then we can show it examples that it has perhaps never seen before by taking audio input, doing the same analysis, and sending it to the neural network. And then the predictions that it makes, the labels that it guesses as the output, will be based on the examples that we showed it before. So it'll make the prediction to say that this new example that you're showing me is most like the oboe examples that you showed me before, or the trombone, or whatever our labels or categories are. And here's the max patch that we'll be starting from. So we have here some oboe multiphonic recordings, as well as some trombone tone recordings. And here's the neural network that we'll be using to do the classification. So the first thing I'm going to do is I'm going to choose an audio analysis to analyze these recordings with, so we have some data that we can use to feed to the neural network. So the audio analysis that we're going to use for this is called MFCCs. I'll make a fluid.mfcc object. MFCC stands for Mel Frequency Cepstral Coefficients, which is a type of audio analysis that's often used for timbral classification. And there's a page on our learn.flucoma.org all about MFCCs, where you can learn more about how they work and what they do. I'm going to put in here the number 13. I'm going to ask for fluid.mfcc to return to me 13 values. And I'm also going to put in the attribute startCoef1. And this is because the zeroth, or the beginning, because we start counting from 0 in these cases, the zeroth coefficient is a measure of the overall energy in the spectrum, so it relates to how we perceive loudness. And in this case, I don't want to be telling my neural network about how loud the sounds are, so I'm actually going to remove that information, that zeroth coefficient, so that the neural network is just looking at the timbral differences between the oboe and trombone. And so by specifying @startCoef1, I'm telling the neural network to, rather than start at coefficient 0 and give me the next 13, which would be 0 through 12, I'm asking it to hop over that 0th coefficient, start at coefficient 1, and give me the next 13, so 1 through 13, and that's what it'll return to me. So if I send some audio into this, we can just see what's coming out of here. Right now it's a bunch of zeros, but if I play some sound, we can see now we have a bunch of values that are describing the timbre in some way. To see that a little bit more clearly, I'll make a multi-slider, which I will set to 13 sliders, so we can see all 13 values. And then I'm going to change the range to about -30 to 30, and that'll let us see most of the range of these MFCC values and how they relate to each other. So if I put this into here and then play some sound, we can see that here's some MFCCs of these trombone tones, and here are some MFCCs of the oboe multiphonics. And we can maybe see that they're different, so we're hoping that they'll be different enough that the neural network will be able to use those differences to do the classification. Now I will make a place to store my data and my labels. So I'm going to make a fluid.dataset. This is where we will put the MFCC analyses. So I'm going to call it MFCC data. And then alongside that, I'm going to make a fluid.label set. And this is where we're going to put the labels, either trombone or oboe, that we're going to pair with the MFCC analyses that are either from trombone or oboe recordings. So here I'll give it the name for instruments. In order to add data to my data set, I'm going to make a message here, add point. And add point takes 2 arguments. The first one is going to be an identifier that we'll use to uniquely identify this piece of data within the data set. For now, I'm going to put in a $1. We'll replace that with the identifier in a moment. And then I need to tell the data set the name of a buffer to look in and see what information is there, and that is the data that it's going to add to the data set. So I'll make a buffer in a moment. We'll call it MFCC buff, since that's the data I'll be writing into my data set. So we'll put this right here, and then we'll better make that buffer. We'll call it MFCC buff, and we'll give it the attribute @samps13. And what this is saying is that this buffer called MFCC buff should be initialized with 13 samples in it. Often when we use buffers in Max, we're filling them with sound files, which very commonly have 44,100 samples per second. So we can have many tens of thousands or hundreds of thousands of samples in a buffer. In this case, we're just going to store these 13 values, the 13 MFCCs that are coming out of this analysis. So we can actually just specify that this buffer should start with 13 samples and will only ever have 13 samples in it. In order to get this analysis into this buffer, I'm going to use an object fluid.list_to_buff, which is going to do just what it sounds like. It's going to take in a list of values and write them right into a buffer. So I'm going to specify @destination will be the buffer that it should write into. That's going to be my MFCC buff. And then I can just connect my analysis directly to this list_to_buff object. And now if I play some audio, we see the analysis is coming through. It's being written into this buffer, and if we check this buffer, we can see sure enough there are some values in there that are getting written into my buffer. Okay. So now we have our analyses in this buffer. We have an add point message to add a point to our data set, which will be whatever is in that buffer when this message gets sent. When I add this data to my data set, I also want to add a label to my label set. So I'm going to make a message over here, add label, $1, which is going to be an identifier to identify this label within the label set. So when we add data to our data set and a label to our label set, we're going to make sure that they are paired together with a shared identifier. So we're going to pass the same identifier to both of these messages at the same time. And then here we need to specify what label should be associated with that identifier. So here I will put a $2, which we will pass in along with the identifier. So the way I will do that is I'm going to make a join object right here. And I'm going to put here a message that is either going to be trombone or oboe. And I'll be able to store that message, either trombone or oboe, in the cold inlet of join here, so that when something comes in the hot inlet, it will pass through the identifier from the hot inlet and the label trombone or oboe. Now to make that identifier, I'm going to make a little series of objects that's going to create an identifier for me and then connect it to these add point and add label messages. So I'll start with a bang. This will be add example. And then I'm going to put here a counter, which will give me a unique integer each time it is banged. And that way I can be sure that all of these identifiers I'm using are unique. Each time I hit the bang, I'll just be able to have a unique integer that will make sure that it will be different from any other identifier I may have used in the past. And then what I want to do is use a combine object to combine this integer with the little word to make this identifier a little bit more human readable, a little bit nicer to look at. So I'm going to call it example dash, and then the S here will be replaced with the integer. So I'll have the word example, a dash, and some number, just to make sure that all of these are identified as different examples. And then I'm also going to give the attribute here at triggers1. And what that will do is turn this first inlet on the right as opposed to the 0th inlet on the left, because we start counting from 0 in these cases. It'll make this first inlet a hot inlet, so that when the integer comes into this first inlet, so that it will replace not the example, but the one on the right here, the S, it'll trigger an output. So if I just put a message here and we see what's coming out, and I hit some bangs, we can see that sure enough, each time I hit this bang, I get a new identifier that is going to be unique. So what I want to do is take that identifier and pass it to this add point message. So now every time I hit this bang, it'll give me a unique identifier, which will get passed to add point. This $1 will be replaced with that identifier, and I will tell the dataset to add a new point to the dataset that is identified as this string. And the dataset should check MFCC buff, and whatever data is in there is what it should add to the dataset. And so when I hit this bang, I will want to make sure that the data in MFCC buff is the data I actually want to add to the dataset. I'm also going to use the same identifier to bang or to send to this join object. Which will be joined together with my label that I've already included in the cold inlet of join here. And then those two items, those two strings, will come to add label. I will have my identifier here, my label here, and I will be telling the label set to add a label to the label set with the identifier that is the same as the identifier just added a data point with, and that it has the label trombone or oboe, whatever I'm adding. Let's see what this error is here. Yes, because I typed something wrong. Okay. So we can start adding data points to our data set with labels to our label set. So I will play some sounds, make sure that when I hit add example, the data that I actually want to add to the data set is actually in that buffer, and I can do that visually by just making sure I have that data here. So here are some MFCC analyses that are from this trombone sound, and I will hit add example while they're in there. And now we can see if that data and label has entered our data set and label set. I'll do that by sending a print message here. I'll just send it to both at the same time. And we can see here on the console that I have a label set that has one row. So just for the one label I've added, it has one column, which every label set will have because it's just the one piece of information, the label. And we can see here that, oh, I forgot to press trombone or oboe, so it added a 0. So let's go back and clear that. And then print it again. Okay, we can see they're both empty. Now we'll make sure to actually store the word oboe into the cold inlet of join here. So let me hit oboe, then play some oboe multiphonics. And while it's playing, add an example. And now print it. Great. And now my example 14 has the label oboe next to it. So here's my, here I'll clear this guy and print it again. So here's my label set, one row, one column. The label is oboe, and the identifier for that label is identifier called example 14. You can see I'm not starting at 0 here. Don't have to start at 0. It's just important that all of these identifiers be unique. And then in my data set, I have one row, again, for that one data point that's been added. There are 13 columns here, which is good because that's how many values are coming out of my MFCC analysis. And those are the 13 values here, which we can see some of here with the ellipsis in the middle. And then the identifier for this data point is example 14, which is good. That means they have the same shared identifier. And when we train the neural network, it will know that this data point corresponds with this label because they have both have the identifier example 14. So now let's add some more data points. I'll make sure oboe's in there just to double check. And then I will play some more oboe multiphonics and add some more points. Just clicking every so often here. You'll notice I'm going to not add points during the silence because, of course, that is not an MFCC analysis of an oboe. So I don't want to add points during that silent bit. And I'm going to stop it right here. So you'll notice I didn't add points during the last 3 multiphonics here. And that's because I'm going to save these multiphonics to be part of my testing set. So the first 5 are going to be my training set, which I will use to train the neural network. And when we test the neural network after we train it, we can certainly test it on these and see how it performs if it's able to identify those as oboe. But of course, it was trained on those, so we should hope that it better get those right. These 3 that we didn't train it on, that were not included in our training set, these will be important to test it on because it will have never seen this data before. It will never have seen MFCC analyses of these specific multiphonics before. So we will be able to see if it's able to still perform well on that data that it hasn't seen before. And this is an important way to test the neural network because we want to know if it's going to be able to perform in a sort of real world situation, right? If we have a oboe player and a trombone player on stage together, maybe they're improvising, taking turns, and we need the computer to be able to identify which instrument is playing, right? The sounds that oboe player is playing, they're not going to be in the training set. It won't have seen those before. So here we're sort of mocking that or mimicking that by reserving some of our data here to test it on after we do the training. So now we'll add some trombone multiphonics, some trombone tones. So I'll hit trombone. So I'm storing the word trombone into our cold inlet of join here. I'll play some trombone tones, add some examples. Again, taking care to not add examples during the silence. And I will stop after this one, again saving about the last third of the data to be our testing set, to test the neural network on after we train it. So now if we print this, we can see that. Here, I'll clear and print. Our data set here has 88 rows. We've added 88 MFCC analyses. They range in identifier from example 14 to example 101. And there are 13 columns, so they all have those 13 MFCC values from the analysis. Then in our data set, we also have 88 rows. That's good. They should be the same because we're always adding them together. They also range in identifier from example 14 to example 101, which is good because we need our MFCC analyses to be paired with a label because of their shared identifier. And then we can see that sure enough, we have the labels in here, oboe, which is the ones I added first. And then at the end here, after the ellipsis, we have the labels trombone. So now that we have our data set here, we can actually train the neural network with it. Here's the neural network that we will use to train. I'm not going to go into what these attributes do. These are some settings that are going to work well for us today. There's a site on our page, learn.flucoma.org, that goes over the MLP parameters and gives a lot more detail about why you might change these and how you might tweak these to train your neural network better. So the way that we're going to train this neural network is we're going to send it the message fit. Fit here is synonymous with train. It's like finding the line of best fit or fitting a curve to some data. And fit takes two arguments. The first is going to be the input to the neural network, which will be our MFCC analyses. We're going to specify the data set that contains all of the analyses we just saved. So it's going to be MFCC data. And the second argument is going to be the output of the neural network, which is going to be the labels that we're asking it to classify. And we've been saving those labels in our label set called instra. Now, before I send this message to the neural network, I'm going to put a message box down here because when it is done training, when it's done with its fit, it's going to report out some useful information for us. So let me just hit this here, and the neural network returns the word fit, saying it has completed that action that I've asked it to do, and it's reported out this value, 0.03. So this value is called the loss or the error, and it essentially is telling us how wrong or inaccurate the neural network yet is at performing the task we've asked it to learn. So generally lower is better because less error will mean it's making more accurate predictions. There's no objective way to talk about this number, like if it's below a certain threshold, 0.01, then we know it'll be good for what we're trying to achieve. But what we can do is we can watch how this number changes over multiple fittings and see if it goes down. And if it goes down, then we know the neural network is in fact improving, having less error in its predictions, and therefore learning from the data that we're showing it. So I'm going to hit fit again and have it do another round of training. It's not going to reset the neural network at all. It's just going to pick up from where it left off, take all of my data, feed the MFCC analyses in as the input, make those output guesses, check if it got them wrong or right. If it got them wrong, adjust itself internally so that it can make a more accurate prediction next time, and then report to me the fit value that it gets. So let me hit fit again. And we can see that sure enough, it went down. Now it's 0.01. So that's good. It means our neural network is improving from the data that we're showing it. I'll do some more fits. And we can see that sure enough, it is decreasing quite a bit. And now we can see at some point it starts to maybe level out, sort of leveling out at this point 0002. Now it's at 0001. We can see if I hit fit here, it's decreasing by 1, 2, 3, 4, 5 zeros, and a 2 was the amount of improvement that we had on that last fit, which is much smaller than, for example, the first fit that we did, or the second fit that we did, where it improved by 0.2. So at this point, the neural network is still improving a little bit, but not as much anymore. It started to level out sort of how well it's performing, meaning that we could keep doing more fits, but we've probably reached a point at which it has learned most of what it's able to learn from the data that we're showing it. So now we might test the neural network and see how it's performing. So let me, oops. The way that we'll do that is we will send a message, predict point. And predict point here is going to take one argument. That's going to be a buffer that the neural network should go and check what data is there to know what data it should use as input to the neural network. And of course, our inputs here are going to be these MFCC analyses. So since we're already writing our MFCC analyses to a buffer, we can just use that buffer. And of course, that buffer is called MFCC buff. So now, if I just press predict point here, it returns to me predict point, saying it has successfully completed that task that I asked it to do, make a prediction given that input point, and it reports back oboe. Now, of course, the neural network is not hearing an oboe right now. It's hearing nothing, silence. But because the labels that we showed it are only either oboe or trombone, it has no concept of any other thing to guess. It can only ever report back oboe or trombone. So it's made the best guess it can, oboe. We'll take a look at how to maybe think about that a little differently in a moment. But first, let's make some predictions. So I'm just going to create a Q metro here to make a bang every 50 milliseconds. So basically, I'm just going to ask the neural network to be constantly making predictions. And now if I start playing a tone, maybe I'll play a trombone tone since we haven't seen trombone down here yet. We can see it's predicting trombone. Oh, and this is actually on some of our testing data, some of the data it hasn't seen before. So that's great. It's working on that information. If I just play it here, we'll see how it performs on these first tones that it actually used in the training. Great, it's getting those right. Trombone. We can see that during the silent bit right here, it got a little confused and reported oboe. Again, we'll take a look at how to fix that in a moment. And of course, that's because we didn't show it any MFCC analyses of silence, so it doesn't even know what to do with that. It's just making the best guess it can, and the guess it's making is oboe. So here are the trombone tones that it hasn't seen before. And it's correctly identifying them as trombone, so that's great. Wonderful. Okay, so it worked on all of those trombone tones. Let's see how it does on the oboe multiphonics. Good, it's predicting oboe for those. Through this silent bit, it still predicted oboe, which is fine. It's actually wrong, though, right? Because it's not an oboe, it's silence. But it's predicting oboe during those moments. Oh, there's a little trombone you saw in that silent bit there, so it got a little bit confused in that silent moment again. Oh, there's some more confusion. Again, because we actually haven't shown it any MFCC analyses of silence. And here are the multiphonics that are in our testing set that it didn't use for training. And we can see that, sure enough, it's getting all of those multiphonics correct as identifying them as oboe. Great, so our neural network here is correctly identifying all of our oboe multiphonics as oboe, all of our trombone tones as trombone, including the ones that are in our testing set, the last third or so of the data here that we didn't use to train it. So one way that we might think about approaching this issue of the neural network being confused during the silent bits here is we might actually just use a different type of measure to identify whether there is sound or not. And if there is, then we should make predictions, based on the MFCC analysis. And if there isn't sound, if there is silence, then we should not make predictions. So one way we might do that is we'll just use a loudness analysis to determine if there is sound present. I would put a fluid.loudness here. send the audio into it. And we'll see what comes out of here is two values. The first one is a loudness measure in decibels full scale, and the second one is a true peak measure, also in decibels full scale. So I'm just going to use the first one, and I'm just going to check if that loudness is above a certain threshold. I'll put a $1 just to get the first element in that list. And then I'll just check and see if that value is greater than, let's say, -30 decibels. And if it is, then I'm going to turn on the toggle to tell the Q Metro to send bangs to the neural network and make predictions. And if it's not, then I'll turn off the Q Metro and not make predictions. We could also just say, have a sort of a toggle here that is going to be either silence or not, so we can sort of know whether that is the case as well. Of course, by silence, I just mean something below 30 decibels. So right now we're not hearing sound, and if I press play here, you can see the silence has stopped. We are hearing some sound, and the neural network is predicting it to be an oboe. If I try some trombone sounds, hearing some trombone here, so the neural network is predicting trombone, and then when the sound goes below that loudness threshold, we have silence again, and then we're making predictions again, that is trombone. So here's our completed MLP classifier, successfully making predictions on a timbral analysis, MFCCs here, as either being a trombone or an oboe, including on the data that we use to train the neural network and the data that we use to test the neural network.